One of the very last things that we're going to talk about in conjunction with stoichiometry is heat. And heat is a little bit hard to understand because it's one of the only things in chemistry that we actually can't measure out on a balance or put into a graduated cylinder. So we really need to start kind of talking about what is this stuff that we call heat. Well, there are a couple different terms that we're going to need to become familiar with as we start to progress into this topic, and two that we tend to confuse, believe it or not. And that would be the difference between temperature and heat. Temperature and heat are often terms that we use synonymously. So we use them kind of one in place of the other, and for most people, they mean the same thing. But let me tell you, they are not the same thing. Temperature, you're probably already familiar with its definition, and we've defined it many times before. It's a measurement of the average kinetic energy of the particles of a substance. We've visualized this many times before by watching particles that are hotter move faster and particles that are colder moving slower. The tool that we use to measure temperature you're also very familiar with. That's a thermometer. So then what about this stuff that is heat? Heat is kind of a little bit weird. Here we go. It is a form of energy. So it's not a measurement, it's an actual form of energy that's used to do other things. And for us in this particular chapter, that thing is going to be to change the kinetic energy of the substance or change the temperature. So heat is used to change temperature, but temperature is not the same thing as heat. If you're having a hard time kind of wrapping your head around this, don't worry, you're not the only one. I have a little visualization for you. So if temperature is a measurement of the kinetic energy, then let's look at two different kind of vehicles. We have a tiny little small sports car and we have an enormous dump truck. Well, if I put the same amount of energy or heat into these two vehicles, they're not going to use it the same way. If they are at exactly the same temperature, just because they're at different sizes means that they're going to be traveling at different speeds. So if they're at the same temperature, they have the same amount of kinetic energy, both involved in both of those chemicals. But the small little sports car is going to do a little something different with that amount of energy than the big dump truck is. So the small sports car is probably going to be able to travel very, very fast and probably pretty far. Whereas the dump truck, because it's just so much more massive, takes more energy to get moving. It might be big, it's going to probably move a little bit slower. So that's kind of how I visualize temperature. Now, just to kind of remember from previous chapter that when we're talking about the different sizes of particles moving at different speeds, that's an application of something that we studied called Graham's law. The bigger you are, the slower you move if you're a molecule. So then how does heat play into all of this? Well, heat is a lot like the atomic fuel that we can put into these two vehicles, and the heat is transformed into kinetic energy or temperature. So in my opinion, heat is kind of a lot like atomic gas, and we can kind of fuel up our little tanks in both of our little vehicles, and then we would see it happening by kind of monitoring the temperature. And I think this is why heat and temperature are often confused. So again, heat is the amount of energy we put into these vehicles. It's transformed into kinetic energy, and that kinetic energy I see as being temperature. So a couple just important things to remember. Heat and temperature are definitely not the same thing. You really can only measure temperature. You can't directly measure heat. And unfortunately, we're going to have to calculate in a backwards fashion to be able to find the amount of heat by monitoring the temperature. More on that in just a second. So one thing that you should also be familiar with is that heat has its own symbol, and the symbol is Q. And the amount of heat that can flow into or out of an object depends on three things. First, it depends directly on the mass of the object. So if you have an enormous object that's really, really super hot, it might take it a long time to kind of cool down. Or if you have a super duper tiny object that might be at that same starting temperature, it might not take as long to cool down because there's just not as much heat on the inside of it. So the mass hugely, hugely affects it. Another way that I kind of think about this is it takes the ocean a much longer amount of time to heat up than, say, a backyard swimming pool. or like the kiddie pool will often heat up faster than the big Olympic-sized swimming pools do. Mass matters. The second thing it depends on is something called C, or the specific heat capacity. And we'll talk a little bit more about that in a second. That's a new term for you. It's a constant, and it's an individual constant for each type of matter. The final thing that the amount of heat that can flow into or out of an object depends on is the change in temperature. So you might only have a very tiny little change in temperature, which means there's not going to be a lot of heat being exchanged. But the larger the change in temperature, it's going to require more and more and more heat to make that temperature change occur. So what is this specific heat capacity thing? Because that's new and that's pretty important. Well, in my opinion, specific heat capacity is an object's kind of unique ability to absorb or release heat energy. You may have seen that if you have two objects that are sitting near a fire, sitting near a heater, one may actually heat up much faster than another, particularly metals. Metals tend to be able to heat up very, very quickly. And that's a unique ability of that type of material. So here's a little example that kind of, helps me. Say you're at the beach, and if you're standing on the sand, that sand might feel really, really, really super hot. So you quick run into the ocean to try and cool off, and that ocean water feels much, much colder. And yet, both of those samples of materials have been exposed to the same amount of energy. What they have different between them is a unique ability to absorb or release that heat energy. It takes a lot more heat energy to make water heat up than it does the sand. So we report that as a specific heat capacity. So let's just say that if we expose the same amount of heat to an object and that the temperature change is high, in order to keep this expression looking right mathematically, that would mean that C, the specific heat capacity, is very, very low. So objects that tend to change temperature wildly tend to have very low specific heat capacities, whereas things that don't change temperature very much tend to have very high specific heat capacities. Let's take a look at an example after we kind of redefine what specific heat capacity is. Now, this is like the official book definition of what specific heat capacity is. It's officially defined as the amount of energy, and the energy unit is joules, Joules, it takes to raise 1 gram of that substance by 1 degree Celsius. So how much energy does it cost you to heat up 1 gram by 1 degree? And let's look at two that you might be a little bit familiar with. Water. Water's specific heat capacity is 4.184 joules per gram degree Celsius. Now what that means is it's going to cost you 4.184 joules of heat energy to heat up 1 gram of water by 1 degree Celsius. And believe it or not, that's quite a lot. Another substance that you might be familiar with would be gold. Gold's specific heat capacity is 0.13 joules per gram degree Celsius. So it only costs you 0.13 joules to heat up 1 gram of gold by 1 degree Celsius. It's a lot cheaper to heat up that gold. Another little example using these two specific materials. When I go to, say, tend a fire outside and I'm putting a log on a fire, my hand tends not to feel that heat energy very wildly because my hand, because it's part of my body, is mostly made up of water. And it takes a lot of heat to heat up that amount of hand by 1 degree Celsius. It's able to absorb more heat energy with a very low change in temperature. But if I'm wearing a ring on my finger, that gold in that ring heats up massively quickly, and it can get to roasting, burning hot in very little time because it doesn't cost a lot of heat energy to heat up that mass by 1 degree Celsius. So although when tending fire, you can actually put a log in the fire and the flames can actually lick up around your hands without really getting hurt, if you're wearing jewelry during that same amount of time, you can actually get burns right where the rings are, right around your fingers. So you got to be a little bit careful. But again, that just speaks to that every substance has a unique ability to absorb or release heat energy. These specific heat capacities are a lot like fingerprints. You can use them to identify substances if you have the ability to go back and calculate for them. Speaking of, let's take a look at a little bit of a sample problem. Since we have an equation, we have some calculating that we can do. So here's a sample problem for you. If 455 joules of heat is transferred into 25 grams of water, what will be the change in temperature? So since we only have one equation at this point to deal with in calculating heat, that is Q equals mc delta T, or Q equals mcat. All I have to do is start to plug and chug. So Q is the amount of heat, that's 455 joules. Mass is going to be that mass of water, 25 grams. C is the specific heat capacity, and I know that that's not specifically given to you in the problem, but they did take the trouble to let you know that you're dealing with water. Specific heat capacities are numbers that you can pretty easily look up in tables or books. I have a sample of them present in a table in your packet that you'd be able to reference throughout the course of this chapter. And that's unfortunately one that you're going to have to really remember. Water's specific heat capacity is 4.184. And that leaves us with only one variable, and that's the change in temperature. So here's what my equation looks like all plugged in. 455 joules for the Q, 25 grams for the mass, 4.184 for the specific heat capacity, and delta T is my variable. And now I can plug and chug that into my calculator, solving for delta T, and I find with 3 significant figures that my change in temperature is 4.35 degrees Celsius.